Okay, hi everybody. Good to speak to you again. So I'm going to get you ready for the final exam now. The last exam we had a lot of math, but we didn't cover the math or the calculations that were necessary in chapters 9 and 10. So that's what we're going to be covering in this exam. Those are the math calculations that you have to do in this exam. The exam is covering everything past the last exam. So it's not cumulative, except in the sense that we're covering chapter 9 and 10, the calculation of relative risk and the odds ratio, as well as their confidence interval. So make sure you understand that. So if you go back to our lecture from the week where we covered chapters 9 and 10, I have that under October 7, 2020. That's where you'll find information about relative risk and odds ratio and how we calculate it. So what I'm going to do in this preview is I'm going to take one example and I'm going to work it out for you. Okay, and this is going to be an odds ratio example, but you still have to do the relative risk. Relative risk and odds ratios are similar. You just have to make sure you understand that relative risk is about incidence, number of new cases, so it can only be used when you have a cohort study design. Odds ratio can be either used when you have a cohort study design or a case control study design. And then I'm going to culminate this by calculating something called the Chi-Square Statistic, which we use a lot in experimental studies. This is not a requirement for this exam. It's extra credit if you do the problem and calculate the Chi-Square correctly. So it's an extra credit problem. So if you want to just stop after I do the example of the odds ratio and confidence interval, that's up to you. But if you want to be eligible for the extra credit, you can do the Chi-Square. Since statistics follows this course next semester, you can do that next semester because we will be covering the Chi-Square in detail. All right, so let me go to our exam preview, and here I'll introduce the Chi-Square first, but I'll just go over everything. So the Chi-Square is used when we want to assess the relation between two variables, and both variables are categorical. So categorical means they're discrete variables. They're counts of some sort, like the count of number of individuals who are positive for COVID-19 and the number of individuals who are exposed to somebody else who was positive for COVID-19. We can calculate that relation between two variables using the Chi-Square. We can also do it with the odds ratio or relative risk. Those are a little bit different. Odds ratios and relative risk are what are known as effect sizes, indicators of effect. And the confidence interval is even better because it gives us some margin of error. Chi-Square is more of a typical test statistic. And test statistics are based on these hypotheses that we set in advance, like the null and the alternative hypothesis. So the odds ratio doesn't really follow that similar rule. It's more of an effect size. So it just gives us an indicator of the usefulness of our result. So we can actually compare it to other studies. So the Chi-Square statistic, and this is what it looks like. This symbol is X, but it's chi. It's a Greek letter, chi, not chi, even though it's spelled C-H-I, right? It's Chi-Square. And it is the summation of the frequency of observed counts within a cell minus the frequency, the expected frequency, square that difference, and then divide by the expected frequency. And we'll calculate that expected frequency using, now I can, next, for those of you who are taking stats, I know that there's at least one person who's not taking stats next semester. She already took it. I'll show you how I can calculate this in a more intuitive sense, rather than just relying on some formula or equation. You shouldn't have to rely on equations. You should be able to reason why these are as they are. But anyway, for now, it's just a total number in a row times the total number in a column divided by the grand total. The Chi-Square is used, it's a distribution, and it follows the same rules like a lot of the distributions we do in statistics, where we can calculate the probability of the observed result given the null hypothesis is true, which is the p-value. And I'll get into that in a second. It's a different kind of distribution. It's like half of the normal distribution. It's because there's no negative chi-square, it's all positive. Anyway, so there's no one or two tail test when it comes to chi-square, because it's only one tail. All right, so let's look at this example. Yes. Okay, so a study is conducted to examine whether education level is related to having regular exercise. Regular exercise is 30 minutes 3 times a week among adults. Okay, got it? So this is a typical type of chi-square problem. But what differentiates it is if I was just counting up minutes of physical activity and using that as my dependent variable, I wouldn't be able to use the chi-square test. But I'm creating a discrete variable here, so I can. So I'm probably dividing up exercise into yes or no for regular exercise. So let's take a look at our table. We want to know if there's a significant relation. We also want to know what are the odds. What are the odds? What's the odds ratio? What's the odds ratio for regular exercise among those with a college degree compared to those with less than a high school degree? So it's, math and statistics is filled with word problems. These are all word problems, the things that people hated when they were in high school. To provide a 95% confidence interval. Okay, so here's our table. We have education. There's 3 different levels. There's less than a high school degree. This row here is just for those individuals who have less than a high school degree. These individuals have a high school degree only, and these individuals have a college degree. So I just used 3 different levels of education. Of course, there can be more, right? We could divide college degree into doctoral, masters, etc. And then among regular exercise, we have yes and no. So the numbers that fill these cells are the nexus of these 2 values, right? So if you have less than a high school degree and you do regular exercising, there's 52 of you, right? So, and if you have a high school degree only and you do no regular exercise, there's 87 of you. There's a total of 44 individuals who have less than a high school degree. There's 152 that engaged in regular exercise, and there's a grand total of 431 people. So this is our table. We can call this cell A, cell B, cell C, cell D, cell E, cell F. There's 6 different cells here. These values in the margins are just total, so we're not worried about those right now. I will say that in an odds ratio, an odds ratio is you can only calculate an odds ratio, for a 2x2 table. So this isn't a 2x2 table, right? Because there's 1, 2, 3, 4, 5, 6 cells, so it's actually 3x2. We always count the rows first. So a 3x2 table would mean there's 3 rows and 2 columns. A 2x2 would be 2 rows and 2 columns. So we can't obviously calculate an odds ratio for a table that's a 3x2, but we can do it for subtables, right? Like I can compare, as I'm asking you to do here, less than a high school degree versus a college degree. So that's 1, 2, 3, 4 cells, and I'm ignoring those who have a high school degree only. So yes, I can calculate an odds ratio here. So we're going to go ahead and do all of this, and you'll see it. I took pictures. All of this will be available for you to look at. So let's get started. Oh, where did I put my pictures? Okay. Let me just open this up. I thought I had them here. Ooh, look. But all the information you need. All right, here's page 1. Okay, great. All right, so let me increase the size here a little bit. All right, let's get started. So here's our table redone, handwritten with my poor handwriting. So I'm only interested in these 4 cells. That's why I put them in little boxes, right? There's 52. So if you recall, an odds ratio is a ratio of odds. So that's number 1. And an odds, or the odds, are the probability of success divided by the probability of failure. Now these are raw numbers, they're not probabilities. And I don't need to calculate the probabilities because honestly, to get, like, say, the probability of being regular exercising if you're in high school is 52 divided by 144. But if I were to do this and calculate this odds ratio like that, these totals would actually cancel out, so I don't need them. So all I look at is the raw values. So odds are probability of success divided by probability of failure. Well, success is subjective here. It's not subjective. It's actually objective. It's whatever the value we're interested in. So I don't equate it to the subjective value. Like if we're calculating the odds of dying, we don't really consider death a success. But in the statistics world, that's the terminology we use. Perhaps it's poorly chosen, but that's for another time and for philosophers to debate. So the odds of well, I actually ask, what are the odds of regular exercise among those with a college degree compared to those with a high school degree? So the odds of success in college in terms of regular exercise is 56, so that's success, because yes, and no is 100, so it's 56 divided by 100. So actually, if you look, sorry about that. If you look here, you'll see I have 56 divided by 100, because that's the odds of regular exercise among college students, and it's divided by the odds of regular exercise among those with less than a high school education, which is 52 divided by 92, and I have that right here, 52 divided by 92. So I have this set up, so it's a ratio of the odds. Now, I have success among those who have a college degree divided by failure among those who have a college degree, and then this ratio is divided by the success among those who have less than a high school degree, divided itself by the failure among those with less than a high school degree. Now, because these are two ratios, a ratio is just division, right? These are two ratios. I should call them quotients, I'm sorry. Let me call them quotients instead. These are two quotients. So I divide the quotient in the numerator by the quotient in the denominator. When I bring this up into the numerator, I can flip it upside down, right, the denominator. So what I end up getting is success among those who are in college times failure among those who have less than a high school degree divided by failure for those in college times success for those with a less than a high school degree. If you're like totally lost with what I'm doing, I'm just multiplying after I could just do it this way, right? 56 divided by 100 divided by 52 divided by 92, or I can bring the denominator into the numerator and kind of flip them around. And when I do that, essentially all I'm doing is this cross product, which is the telltale, well, not the telltale, which is the fundamental way to do an odds ratio. So it's 56 times 92 divided by 52 times 100. Okay, so if this is confusing, you don't even listen to me there. Just do success divided by failure among college students divided by success divided by failure in those with less than a high school degree. It's fine. Either way is fine. All right, the equation for, well, so this is your odds ratio. We just calculated it. It's 0.991. Now, if you recall, if an odds ratio is less than 1, that means, it's sort of, it kind of goes, it's counterintuitive what we would have thought in this case, because we would have thought that being in college, you'd be more likely to exercise than people who have less than a high school degree, but this is not so. A value of 1 means there's no relation at all between the two. So in other words, there would be no relation between education and exercise. And this is really close to 1, so it's kind of leaning towards there's probably no relation between the two. But we have to calculate the 95% confidence interval here. So the odds ratio itself is not normally distributed. So in order to deal with that, so a normal distribution is this beautiful bell-shaped curve. So to deal with that, we take its natural log. The natural log of a value will actually normalize it, make it look a little bit more normal. It flattens the curve a little bit. You should be used to that terminology now because we keep hearing it all the time, flattening the curve. So this equation, and so because I bring it into this natural log scale, I have to bring it back to the odds ratio scale when I'm done. So I'll end up exponentiating. This is on your calculators, this E value. So I need the natural log of the odds ratio, and we're going to add and subtract because we're doing the confidence interval. The confidence interval surrounds what's known as a point estimate. This is known as a point estimate. It surrounds it. We need the margin of error, and the margin of error is going to depend a lot on what we choose to be our acceptable false positive result. And this is something known as alpha. And again, if this is all sounds horrible to you, we're going to talk about this a lot more in stats. But right now, just know that this critical value is 1.96, and then you have to multiply that by the standard error. So we've already covered this. This is just a review. Standard error for an odds ratio is 1 divided by A plus 1 divided by B plus 1 divided by C plus 1 divided by D, where these are the 4 cells, right? So there's 4 cells here. You can label them A, B, C, D. It doesn't matter which ones go first when it comes to the calculation of the standard error. All right, so I go ahead and get the natural log of the odds ratio. So that's minus 0.0009. If you're having a hard time understanding what that is, so in a scientific calculator, ln is the natural log, right? So ln is the net. So let me just take a quick look at this here again. What our value was, it was 0.991. So I take the natural log of 0.991. Oops. So I'd have to put 0.991 in here. 0.9. Let me clear that. 0.991 and take its natural log. And so that's what I get, negative 0.009. By the way, that exponentiation is doing this. So it'll get us back. So you see how they're related? One is the inverse of the other. So that's why we do it again in the end, because we want to get it out of the natural log scale. So let's go back here. And yes, we got minus 0.009. And I went ahead and did this calculation. So each of these this is a summation of these inverses right here. And what do we get? We get minus 0.009 plus or minus this value 0.0471857. Next step I do, and you should do this whenever you do this kind of calculation, is just separate them into the lower confidence limit and the upper. But notice that I still haven't, so this is an exponential function, I still haven't finished it here, right? So I get e to the minus 0.480857 and then e to the 0.462857. The reason I have two of them is because I have a plus or minus, right? There's a minus on the left side and a plus on the right side. So you're subtracting from the log odds on the left side, and you're adding to the log odds on the right side. So I get, once I exponentiate them, I get 0.618 and 1.587. By the way, because this is really important actually, because these cross 1. What I mean by cross 1, so this is below 1, right? 0.618 is below 1 and 1.587 is above 1, right? So 1 is somewhere in here. We could use just this result alone to determine statistical significance. This is not statistically significant because it includes an odds ratio value of 1, which means they're not significant. Now, odds ratio is a ratio of odds. If the odds are the same divided by the same is going to equal 1. So it's not significant. But we'll worry about that later. Let's go to the next. If I could go to the next slide. And okay, I guess not. So let's go to the next slide. All right, so now I want to calculate the Chi-Square Statistic. All right, so I rewrote down the table here. Chi-square is a test statistic. We have to start with a null and then introduce our alternative hypothesis as well. So our null hypothesis is that there's no relation between education and regular exercise. Since I'm not calculating an odds ratio here, I am using all 6 of these cells now. The alternative is that there is a relation between education and regular exercise. So I rewrote my chi-square equation here. Now I have df here for degrees of freedom, and I also have this summation with I equals 1 to c. This capital C is the number of cells. So in this case, there are 6 cells. So I'm gonna add. Sigma means summing, means adding. I'm gonna add this 6 times basically. So I'm going to do the observed by the expected value. I'm going to square it divided by the expected value for each cell. I'm going to do that 6 different times because there's 6 different cells. We need the degrees of freedom because that'll allow us to find what our critical value is, so we can either reject or fail to reject the null hypothesis. To calculate the degrees of freedom for the chi-square, it's the number of rows minus 1 times the number of columns minus 1. So we have 3 rows, right? 1, 2, 3 rows. 3 minus 1 is 2, and there's 2 columns. 1, 2, 2 minus 1 is 1, so 2 times 1 is 2. So if we go into any textbook, or if you just Google online, I need a chi-square table, you have to be able to look up the critical value, and I think I might still have this up here. Do I? No, I don't. But you can go into and say, you know, I think I did on my phone. That's why. Chi-square table. You know, just find some table, some generic table somewhere. I don't know which one will be the best. Let's see. I think I used something like this. Yeah, let's see. Well, actually, I can tell. I need to see the whole table. Yeah, here's the table. This one tells you if you have 2 degrees of freedom and your alpha is 0.05, and again, we'll talk about this in stats, the critical value is 5.991. If we just did a 2 by 2 table, our degrees of freedom would have been 1. If our alpha is 0.05, we would have had 3.841. But in this case, it's 5.991. So I went ahead and wrote that down here, right? Chi-square for 2 degrees of freedom is 5.991. Okay, we have the observed counts. That's the observed counts are what we see in these cells. So this is the observed count for this cell. It's 52, right? The observed for this cell is 92. So now we just need the expected counts and calculating the. So I rewrote this table here, and you'll notice that I labeled each cell. So this is cell 1, 1 because this is row 1, column 1. This is cell 1, 2 because it's row 1, column 2, and this is cell 2, 1 because it's row 2, column 1, etc. Okay, you should be able to figure that out after I mention it. The equation is row total minus column total divided by the grand total. So for this cell here, cell 1, 1, the row total would be over here and the column total would be over here. So let's go ahead and look at this from the up here. For cell 1, 1, the row total is 144 and the column total is 152. So to get the expected value would be 144 times 152 divided by the grand total, which is 431. So we've got 144 times 152 divided by 431. I'll do one more and then I'll just show you. So let's do let's say cell 2, 1. So cell 2, 1. So row 2, column 1. So you do the crisscross here, right? So they crisscross at 44. So the row total is 131, the column total is 152. And that's what I have. 131 times 152 divided by 431, and I get 46.1995. You'll notice that sometimes I have more numbers after more decimal places. That's because I'm just trying to get good precision. So I do this for all 6 of the cells. Finally, what I do is I'll get the difference between each cell's observed value and its expected value. Well, we know the expected value for cell 1, 1 is 50.784. We go to the observed value and it's 52, right, for cell 1, 1. So I'll go observed minus expected. I'll square that divided by the expected. I do that for all 6 of these values. So that's what you have here. You've done for all 6 of the values. And then let's go to the last picture here. So what I do then is I just add all of these up. Oops, that's a little too big. I add all of these up and I get 0.233947, and now I like to present them in 3 significant figures. I get 0.234. Well, since 0.234 is less than 5.991, I would fail to reject the null hypothesis. Now, the decision you make here is based on the relation of your calculated value to the critical value. Our critical value is 5.991. To be significant, the calculated value would have to be greater than or equal to the critical value. Well, this is much smaller, so we fail to reject the null. So we cannot conclude that there's a relation between education and regular exercise based on these data. It's based on these data only, and that's supported by the confidence interval around our odds ratio that we calculated. So that's what you need to do in order, to get the extra credit is the chi-square. Everything else is part of regular credit, as is the relative risk. We didn't cover the relative risk here because we already did that, and I think you're pretty good with that. All right, thank you everybody. Bye.